Alrighty, my name is Tony VE3 and I don't ask you to pronounce that, but it's a Dutch name. And what do we have? Oh, we got markers and everything. Great. Do I print large enough? Oops. This is not about religion, this course, but I do put that down. 3 items that I always mention before I start in the course, or I make myself blue already, is not necessarily in this order. Energy, be here, and I probably will make these expressions as well during the 3 evenings that I'm going to be here. That comes up, and you'll see it in the book as well. It says energy is getting lost. Well, there's no such thing as energy getting lost. Energy, keep that in mind, because you will need that for the next week for capacitors and inductors. Energy cannot be destroyed. Energy is not being lost. Energy that disappears on you is converted or transformed in a different type of energy. So energy cannot be destroyed. So keep that in mind. Secondly, questions. If you have questions, you ask. You stick up your hand, you throw your water bottle at me or whatever, get my attention. The only dumb question is the question that's not being asked, so don't be shy. Secondly, religion. Now the only reason I mention that is some aspect of electronics we can't get our head around, we do not understand it. You say, you know, how can that be the case? How can that happen? So in some aspects, electronics is a little bit like religion. You just believe that it is so. You know, without question, you accept it. So now we have established these 3 points. We're going to talk tonight about Ohm's law. And Ohm's law is a couple of formulas that define what happens when you have resistance and voltage and current. Now we all know what resistance is. When we were 12 years old and we wanted to go out for an evening with the girls, your parents resisted you. They didn't want you to go. That's a form of resistance. There's many forms of resistance, but in our case, in electronics, when we talk about resistance, we're talking about a piece of equipment, an item, or anything that opposes what you're trying to do. What that is opposing what you're trying to do. It's resisting it. So, we have resistors in electronics. And I believe in last week's lesson that, or Tuesday's lesson I should say, that it was talked about resistors and the type of resistor materials, aluminum, gold, silver, copper, various other ones, and insulators, insulators that present some resistance, and other insulators that present so much resistance that there is no current flow at all. The most common form of wire that we use with the least amount of resistance that is affordable would be copper. You can have iron or steel or whatever, or aluminum. They are all conductors. But they do have some higher resistance than copper. Copper is one of the best conductors. Silver is better, but it's a lot more expensive. Contrary to beliefs, gold is not a very good conductor actually. It's expensive, of course, but gold has a characteristic that it resists corrosion. So when you see circuit board cards, and on the end where the fingers are that go into the connector, the ends of the pins, they may be gold plated, and the only reason they're gold plated is because it resists corrosion, not because it's such a good conductor, but it's good enough. Okay, resistors come in all kinds of forms. Carbon resistors, wire wound resistors. You have seen pictures in your book, no doubt. And before I go any further, I expect everyone to read the chapter that you're going to be getting next week. So you're going to be studying already the chapter for capacitors and inductors, which is what we'll do next Tuesday. So we have variable resistors. This is a tiny one. It's called a potentiometer. Here's another one. It's a double one. We may not have seen the part on the back, but we've seen this with a knob on it and your stereo. The one in the center controls the volume, and the one on the outside it may be a tone control or a bass control or whatever. Here's another one, the variable resistor. So we'll go into this a bit more into detail. Here's more like a high power resistor. It's a ceramic body with a wire type resistor in it, and it can withstand a lot of heat. Same as this one. You can tell usually by the way they look like. We'll pass them around in a moment. Okay, a resistor. It's a bit like a hose that you use for sprinkling your garden. If you want a certain amount of water to come out of the hose, you take a certain size of hose, or what you normally have is a regular size. You turn the water tap open, and the water pressure that comes out of your water tap dictates how much water is coming out on the other end of the hose. If you want more water out of the other end of the hose, what do you have to do? Either turn the tap more open if you didn't have it open all the way, or you got to increase the water pressure. That way you get more water out of it, because the hose is like a resistor. It resists the flow of water. Another thing you can do to make it less resistant is increase the size of the hose. You may not get necessarily more water if you keep the voltage the same, but at least it flows a little easier. So, resistor, the symbol of resistor that we use is a squiggly line like this. That's the electronic symbol on the schematic. If you see schematics that come from Europe, you may see the resistor drawn like this. Okay? But here in North America, we generally use this kind of symbol for a resistor. Resistors have a value, and the value that the resistors represent is an indication of the size of the resistance that it presents to the voltage, and as a result the current that will flow. Now, the part that determines the amount of water or current that flows through it is the voltage, and the symbol for that is E. Stands for EMF, electromotive force. So, and it is expressed in volts. There was a gentleman by the name of Volta who discovered this, and that's why the name volts was chosen to represent that EMF, electromotive force. You probably all heard about his experiment that he found out that the frog legs hanging on the wash line dingling in the wind, and it touched a copper wire or an aluminum piece of wire, and the frog's legs were moving. The muscles contracted. That was a result of electricity flow. And according to that, that's how we discovered an electricity flow, etc. The amount of current, the strength of the voltage of the current going through the resistor, the symbol for it is I for current, and it is measured in amperes. In short, we usually call it amps. And the resistance of a resistor, whether it's a wire resistor or a light bulb or whatever, is called R for resistor, and it is measured, the symbol here is omega, and it is written like this, ohm. I think there was also a gentleman by that name, and the same as ampere, it was also a person. So over here we have the three characters that we find in Ohm's law: E for voltage, I for amps, and R for resistance in ohms. Boy, my mouth is getting dry already. There's a relationship between those three. You cannot change one without changing the other. If you change one of them, there will be a different, depending. A resistor, you normally is a fixed resistor, you leave that. But if you change the voltage, what will change? Not the resistance. A resistor of a certain size is fixed. You don't change that during the operation. But if you change the voltage, the resistance is the same. The current has to change. That is part of Ohm's law. If you change the amperage, more or less current, the resistance again remains the same because we have a fixed resistor. What does change then? The voltage has to change. There's no ifs, ands, or buts about it. Now the official formula for Ohm's law, we know all this of course already by heart because I'm sure we all studied that. And you gotta know this, you gotta remember this. E for volts, I for current, R for resistance. It's gonna be on the exam. Ohm's law, E volts equals I So when you see that without the X, don't despair. It means I times R. And Ohm's law states that if you have E and you have R, you can figure out I. Okay? I equals E divided by R. And the opposite is true. If you have the resistance and you have the voltage, then you can figure out the current. But if you have the voltage and the current, you can figure out the resistance is E divided by I. So these are the three formulas that consist of Ohm's law. You have to know these. Remember them, learn them by heart. It's not very hard. It is in your book. But there's an easy way to remember this. Very easy way to do that. I provided you all with two sheets, and one of them shows these nice circles. The one on the left hand side is for DC voltage and DC current. The one on the right hand side is for your interest. You don't have to necessarily follow that. But the one on the left here is very easy to use. There's for the standard Ohm's law, there's a very easy way of finding out the formulas and remembering them, figuring them out. E I R. Learn that by heart, because then you don't have to remember each individual formula. You can do that, of course. But this tells you that E, voltage, is I times R. R is voltage E divided by I. And I, current, is voltage E divided by R in ohms, the resistance. So this line tells it all. I times R is E, E divided by R is I is R, E divided by R is I. So that's not very hard to remember. Okay, we have a number of resistors. 1, 2. I'll start off with 2. Let's give them a value. Let's say this one is 6 ohm, and we don't write down 6 ohm. If this is 6 ohm, the normal form of putting that down is 6R. And when that says 6R, that means it is 6 ohm. But I'm going to leave that out to make it less confusing. So it's 6 ohm, and this resistor here is 4 ohm. Now if you have a garden hose of 20 feet long and you have your tap all the way open and you know there's a certain amount of water coming out of the other end of the hose, you're going to put an extension of the same size hose another 20 feet long. There's more resistance. You're going to get less water pressure coming out of the end. So you have to add the resistance of both hoses actually together. That's the same with this. If you have 2 resistors and you put them in series, which means you connect the one side of the one resistor with the other side of the other one, you're going to essentially have one bigger resistor. So the total value of the 2 resistors in series is the value of the one plus the value of the second one. So we can substitute these 2 resistors by adding them together, and now it becomes one resistor of 6 plus 4 is 10 ohms. Everybody understands that? Okay? It's logic, right? You can see it when you add those 2 resistors together. You can go on ad infinitum with that. You can have 2 resistors, 3 resistors, 4 resistors, 5 resistors, 100 resistors, n resistors. When they are in series, to get the total resistance, you just add them all together. Okay? Now there's another way of putting resistors together. This is called series resistances, putting them in series. If we have 2 resistors, if we don't put them in series, we have 2 resistors, and now we're going to put them in parallel. So connect them together on the ends. And to make it easy, we'll make this one 10 ohm, and we'll make this one 10 ohms. Now what do you think is going to happen when we added them in series? We added them together. If we're going to put 2 of them in parallel, it's like putting 2 garden hoses of the same size in parallel. You connect the beginning end and you connect the other ends. What do you get? You're going to get a garden hose of twice the size of each, right? So it's going to be a lot easier for the water to flow through it. You're going to get more water coming out of the other end, or at least it has less resistance. So if you put 2 resistors in parallel, you actually are going to make a resistor that is smaller. Now with resistors of the same value in parallel, it's very easy. You just divide the value by the amount of resistors that you have. So in this case we have 2 resistors, so you take the value of 110 divided by 2, and the total resistance of these 2 in parallel now becomes 5 ohms. Does that make sense? Okay, good. I'll make it a little easier again. I'm taking another resistor here in parallel. So now we have 3, and we'll also make this to make this 9 ohm, and this one is 9 ohm, and this one is 9 ohm. The same idea counts here. You now have 3 resistors, and because all resistors have the same value, and you can only do this with the resistors having the same value, you take the value of 1, divided by the amount of resistors, 1, 2, 3, 9 divided by 3, so now you get 3 ohms. So the total resistance of is 3 ohms. One thing that you will discover when you do that yourself too with other values, and what you can see clearly here is that the resultant resistance, the total resistance, is always less than the value of the lowest resistor. Now here they're all 9 ohm. So it's quite easy to see that the total resistance will always be less than 9 ohm. In this case it's 3 ohm. But if you had, for example, here a resistor of 50 ohm, and here we have one of 20, and here we have one of 8. Well, we don't know what the resistance of this is. We'd have to calculate that. But what we do know is that the answer has to be less than the smallest of the 3 resistors. So the answer will be less than 8 ohm. If you do the calculations and you come out with a value that is larger than the smallest resistor, guaranteed you made a mistake. So keep this in mind. Resistors in parallel, the resultant resistance value is always less than the smallest of the resistors in parallel. Now there is a way, of course, with these odd values to figure out how to calculate that. Now we all are familiar, I'm sure, with calculators, and you are allowed on the exam to use a calculator, except it cannot have a memory and it cannot be a programmable calculator. So you can use a basic calculator that has percentage, square root, etc., pi, you name it. As long as you cannot store anything in there beforehand that you could use during the exam, like a formula, you cannot do that. But you are allowed to use a calculator. So I'm going to show you 2 methods of doing calculations of resistors in parallel. Again, resistors in series is no hardship at all. It's very easy. When you put 2 resistors in parallel, there is a formula, and I call it R total, or they sometimes call it R equivalent, but I personally like R total, equals R1 times R2 divided by R1 plus R2. Let's make it less confusing and take this out of the equation here. So when you have 2 resistors in parallel and they're not of the same value, you know now that if there are the same value 2 resistors, it is half of the one value. But with 2 different values, you take R1 times R2 divided by R1 plus R2, and that gives you the resultant, or R total, of 2 parallel resistors. Okay, somebody gets a calculator out and we'll put this to the test. R1 is 25 ohm and R2 is 12 ohm. Okay, somebody has a calculator and calculates R1 times R2. 300. How much? 300. 25 divided by 12, times 12. Okay, 300. So we do 300. And now R1 plus R2, that's not too hard, that's 37. Okay, so then divide 300 by 37, and what is the resultant answer of that? 8.1. 8.1. Now I had used, what was it, 25 and 12, right? What do we see immediately? The resultant, the total resistance is less than the smallest. So you know that you're, even if you're not quite correct, you're in the ballpark. But since you have done the calculations with your calculator, you can pretty well be assured that you did that correct. So 300 ohm in parallel with, 300 ohm, 25 ohm resistor in parallel with a 12 ohm resistor. The total resistance, when you put the two together, make it into one, is 8.1 ohm. All right, works great. Now, let's do this again. Okay, now I have three. I'll make this 50, I'll make this 12, and let's make this 17. And they are all in parallel. And if you do it properly, you should put a dot there so that it indicates they are connected. In some schematics, in order to make sure, like when you see this, you're not sure whether they are connected or whether this just goes further. So when you put the dot there, you know they're connected. And in some schematics, different countries, I'm not sure which one, what they do is they either go with a little bow around it, so now you know it is not connected, it jumps. Okay, so now you know it's not connected. But in order, if you don't put the dot in there, and it sits like that, and to make sure you go like this. Now you know they have to be connected. Okay, you don't see that too often. I see, and I always use the dot in there. Makes it a lot easier, leaves no doubt about it. Okay, now we got three resistors in parallel. How are we going to do that?
Two ways, I guess. You could do the equivalent of the 50 and the 12.
Right.
And then do the equivalent of that with the 17 using that formula.
Exactly.
The 1 over our total equals 1 over
yeah, we'll get to that in a moment. Now, you can do this with an infinite amount of resistors in parallel. You can first take these two. So you do R1 times R2, if you call this R1, R2, R3, divided by R1 plus R2, and you get a result which becomes then one resistor. So what do you have now? You now have two resistors in parallel. And you do the same formula over again. And you get the resultant, the total resistance, that way too. But that means you'll have to do this calculation twice. If you got more resistors, you got to do it again and again and again. So you follow that, Joe? Okay. Remember, we said if you want to have to calculate two resistors that are in parallel, you use this formula. If this is R1 and this is R2, you take R1 times R2, 50 times 12. How much is that? 600. Okay. Then we take R1 plus R2, 50 plus 12 makes it 62. So you divide that by 600 by 62. How much is that? Anybody done that calculation? 9.6. Okay. So now we can take both of these resistors off and make only one resistor which has a value of 9.6 ohm. Yes? Okay. We take 50 times 12 is 600. Top part of the formula. The bottom part of the formula is R1 plus R2, so that's 50 plus 12 is 62, right?
Okay, I thought it was 600.
No. So R1 times R2, R1 times R2, 50 times 12 is 600. You calculated that correctly. Now R1 plus R2 is 50 plus 12 is 62. So now we follow through by dividing 600 by 62, and the answer was 9.6. Can you do that on your calculator? 600 divided by 62? Okay, alrighty. So now we actually have gotten rid of this one here, let's say, and now we have only two. This one is 9.6, this is 17. Now we go through the same exercise again. We take now R1, which is this one here at 9.6, times 17. How much is 9.6 times 17? 163.12. 0.2, okay. 163.2, and then we get 9.6 plus 17, that should be 28.6, sorry, 26.6, is that correct? 9.6 plus 17, 26.6. Okay, 26.6. So somebody use that on the calculator. 163.2 divided by 26.6 is what?
6.135.
6.135. Okay. 6.1, oops. I'm running ahead of myself here. So since we have 6.135, we'll round it off at 6.14. So now we have the total resistance of these three in parallel, and it became 6.14 ohm. What did we see right away again? It is smaller than the smallest of the three resistors. The smallest is 12. This is smaller, so we can pretty well say that we are in the ballpark, and if our calculator is working fine and you press the right buttons, you got the right answer. Now if we had another resistor here again, we already know the resultant of those three, 6.14, and this one is 5. You can do the same thing again with that. So you do all the iterations, you do them one after the other, and you get to the result.
Doesn't matter which order you do them in?
No, no, as long as you take two that are adjacent. Well, it doesn't matter. You can take this one and that one, and the resultant one becomes just one, and then you can that. So
it doesn't matter which
no, because they're all in parallel.
Okay.
They're all on the one side connected with each other, so it doesn't really matter. But it makes it easier for yourself to take, let's say you start at the top, you take these two, then that becomes one, then you take that one with this, becomes one, and then you take this and this, and you have the end. So you can take any order of those, but it probably makes it more confusing for yourself. Yes?
Is there a quick way of estimating the overall tolerance if you wouldn't added all your resistors together?
What do you mean by tolerance?
Like say the tolerance on number 1, 50 ohms is plus or minus 5%, and the other ones are 10%.
Oh, yeah, that has absolutely nothing to do.
No, you can't. So you can't
No,
estimate that.
tolerance doesn't come into the picture here at all. Tolerance is something totally different. Yes.
So, what is the purpose of this? Wouldn't it just be more useful to use a smaller resistor versus going parallel, or is that what you
That's well, there you go. Let's say that you have a piece of equipment and it requires a 6.14 resistor, which you do not have. And Radio Shack doesn't sell that value either. But you have found out through engineering or whatever that value has to be 6.14 ohm, otherwise your piece of equipment will not work properly. So how the hell do you get that? Well, you go through your junk box and you have I don't know how many resistors, and it is time consuming, but eventually you can probably come up with maybe 2 or 3 or sometimes maybe even 4 resistors that when you do them like that in parallel, you can come up to that. Let's say you have 2 resistors of 3.07 ohm. You put 2 in series and you got 6.14 ohm. So whichever way you do it, putting them in series, putting them in parallel, or series parallel, you can come to any value. So that's really, now this is definitely something that you may come across in real life. You may have an amplifier and it has various stages, and they're all operational of a voltage power supply, but each part of the stage represents a certain amount of resistance, and they are in parallel or in series. So that's why you need to know this.
Different resistors can give you different tones on sound, or is it just not an effect?
Yeah, that can. Yeah, if you have an RC, what's called a resistor capacitor combination oscillator, then the tone can be varied by changing the value of a resistor or of the capacitor, or two in tandem.
So somebody making an amp might want to make it sound a certain way, so they stick a bunch of parallel like that to get a specific sound.
You could, yeah, you could. But likely the engineer who designs the amp is not going to use 2 or 3 different resistors. He'll probably calculate the system as such that he can take standard value resistors.
And as a general rule, do you use the same power rating for all your resistors?
Not necessarily. We'll get to that later. But you can use always resistors that are higher in power. It's in our case, it's the value of the resistor that counts. But let's say originally they are all 5 watts, and this one burns up, you got to replace it with another 50 ohm. You can put one in that's 10 watt. Doesn't matter, as long as it is greater than the original one power rating. Okay, so we figured that out. There is an easier way to do it, but you got to remember that formula, and it really is not hard to remember. There is a formula here that is 1 divided by R total equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, etc., etc., etc. And we'll take this one out of here. Let's do that. So in the calculator, you make sure that the registers, that it is all clear, and you put in there 1 divided by 50 equals, and you get the answer. Then you hit memory plus. Then you clear it, not the memory, you clear the screen. Then you go 1 divided by 12 equals, and you hit again memory plus. See what you do here? R1, you put it in memory, then you add the second one. Then you take 1 divided by 17, hit equal, memory plus. So now you have done these 3 calculations, 1 divided by 50, 1 divided by 12, and 1 divided by 17, and you've added them together in memory. Okay? So now you do 1 divided by memory read, and you got your answer. Somebody do that in the calculator?
So sorry, what is the RT?
R total, the total resistance, or the equivalent resistors of the 3, the 3 in parallel. So the 1 divided by 50, and then enter that into your memory plus. Now hit clear once or twice, whatever. And then you hit 1 divided by 12 equals, and add that to memory. And everybody can do that if you wish. You don't? Well, go to Walmart and spend $6 and you have a scientific calculator if need be. But and then after that you do 1 divided by 17 and memory plus, and then you do 1 divided by memory read, and what is the answer?
Final answer?
Yeah?
6.17.
Okay. See, we came here at 6.13 whatever. We did that, so that's close enough. Let's see if we... no, I got my... Okay, I'll take my trusty cell phone Okay, we said 1 divided by 50, 1 divided by 50. In a lot of calculators, when you now hit memory plus, it automatically puts the answer in there. But let's do it. Equals 0.02. So I hit memory plus. I clear it. I now say 1 divided by 12 equals 0.083333. And I add that into memory plus. Clear it. 1 divided by 17 divided by 17 equals, put in memory plus, and I clear that, and now I say 1 divided by memory read equals 6.1668686, etc. All right? Memory clear. Don't forget to clear memory if you have more calculations to do, so you don't add them all together. Okay, any questions about this? This is essentially the formula you got to remember. I'll take this out to make it less confusing. If you have more than 2 resistors in parallel, or more than 3 or 4, you can do it the way with R1 times R2 divided by R1 plus R2, and do that over and over and over until you get to the bottom. Or you do it this way: 1 divided by R total equals 1 divided by R1, 1 divided by R2, 1 divided by R3, 1 divided by Rn, however many you have. And then when you have that into your memory, then you go 1 divided by the memory read, and it gives you the answer. Okay? You understand all that? Okay, now we have done series resistors, we have done parallel resistors. What do you do if you have a combination of them? Does that look tricky? Maybe it does, but it doesn't. I should. So you're going to do the process of elimination. Here you have 2 resistors in parallel. We're going to make it easy. We're going to make that into 1 resistor by doing the calculation of R1 times R2 plus divided by R1 plus R2, and you end up with the value of the resultant of this. So it actually becomes 1 resistor then, okay? So now, and I did it this way, I drew it like that, but for the same token I could have put it from here to there, right? So you would have had these in parallel with each other. These 2 are in series, so you add them together to make 1 resistor. I should give you some values, just for the heck of it. And we'll make this easy. We'll make this 5, and we'll make this 5, and we'll make this 10, and this one we make 3 and 7. So to do the result, the calculations, you first calculate these 2 together in parallel. You take 5 divided by 2, it's 2.5 ohms, right? So now we have 1 resistor here, and it's already made it look more familiar, and it is 2.5 ohms. Now we have here 3 ohm and 7 ohm. Well, make that into 1 resistor. You add the 2 together, and it becomes 1 resistor of 3.7 is 10 ohm. So now we have 3 resistors in parallel, 10 and 10 and 2.5. You can do these 2 easily because you know they're 2 of the same value. So you take 10 divided by 2, and it becomes 1 resistor of 5 ohms. So now we're left with a resistor of 5 ohm and a resistor of 2.5 ohm. And we do that with our calculator, or you do that 5 times 2.5 divided by 5 plus 2.5. So we had 1, 2, 3, 4, 5 resistors here in parallel, one in series. We've calculated that to one resistor of, what was the outcome? Did anybody do this calculation? That should be 12.5 divided by 7.5. That's less than 2. But anyway, so we had this here, and it became only one resistor. So now we have, and I didn't give values to that, but let's say this turns out to be 2.3. It's a wrong value, but let's put a value there. So now you've eliminated that whole thing into 3 resistors in series. 5 and 2.3, 7.3, and 5, 12.3 ohms. So you've broken down that whole series of resistors. First you added the resistors in series together, and then you started to calculate the ones that are in parallel. And the 2 on the outside, you add them to last. So you end up really with 3 resistors in series. Does that make sense?
The ones in parallel, what did you come up with for your?
Oh, I forget what I came up with.
One came to 5 and one came to...
I was guessing.
Yeah, I was guessing. I didn't use the cal. I just put an arbitrary figure down. We could have calculated that, but at any rate, so that's how you do it. Multiple resistors in parallel and series, a combination. You always break them down. First, the ones in parallel, you break it down to one resistor, and then you are going to end up with resistors in series only, and you add them together, and you got it done. Alrighty, what time is it? 10 to 8? Oh, let's have a little break.